It is now my pleasure to introduce Dr. Tarasankar DebRoy, who is a professor of material science and engineering at Penn State and the author of many papers and a new book from 2021 on innovations in everyday engineering materials. He has served as a Fulbright Distinguished Chair in Brazil, a Distinguished Visiting Professor at IIT Bombay, the Aditya Birla Chair at Bangalore, United Kingdom Royal Academy of Engineering. He's been a Distinguished Visiting Fellow at Cambridge University and a Visiting Professor at KTH Stockholm. He is a founding editor of the journal Science and Technology of Welding and Joining. And as you can see from his title talk here, he has made innovations in material science in just about every area. So Dr. DebRoy, thank you for being here.
Thank you so much, and good morning to all of you. 3D printing or additive manufacturing is gaining wider usage in a number of industries. We did a survey about 3 years ago in different industries ranging from consumer products to automotive to healthcare to energy to aviation to marine industries, and published our results in Nature Materials. And a case in point is this fuel nozzle that General Electric uses in their jet engines. This nozzle used to be made by assembling 20 different components. Today it is made by a single process in Alabama. Another case is the left lower picture, in which this is the inside of the International Space Station. They needed a wrench to fix some problems, and there was no resupply mission planned at that time. So NASA sent a computer file to a desktop printer, and the desktop printer printed this wrench in 102 layers inside the International Space Station. The reason it is getting so much importance is because there are some parts, like the one on the top right-hand side that I'm showing here, that cannot be made by any other ways. I want to talk a little bit about the 3D printing and how to solve many of the problems in a way that is different from how we used to solve problems in welding and casting and other metals processing operation. I want to point out some of the opportunities in 3D printing for people interested in AI. We have been also doing mechanistic modeling based only on physics, and I'm showing a picture here from our recent review in Nature Review Materials published last year. And also, I want to talk a little bit about how we can mix the mechanistic modeling with machine learning, and talk with you about how physics can empower machine learning from our own work. And finally, I want to finish by pointing out our main contributions and outlook. A few words about metal additive manufacturing. There are a number of variants of the process, but all of them would make a three-dimensional part by adding thin layers of materials, layer by layer. Parts may be very complicated. They may have site-specific chemical composition or complex internal cooling channels. And what is most important, perhaps, is that the same equipment can produce a diverse array of components on demand. That means there is no requirement for a minimum production volume. You can make one or you can make 1,000. Powder bed fusion is where we prepare this intricate part. I'm showing here the Nittany lion, which is a mascot for Penn State. And we are using here a laser beam. We supply a very thin layer of powder, sometimes thinner than a human hair, to make this intricate part layer by layer. Sometimes we supply the powder coaxial through the laser beam and make a powder on a substrate. Or when we need very high productivity, we make use of a gas metal arc heat source, and we supply consumable wire to make large parts quickly using a process which is like a multi-layer welding process. But here is the difficulty. It's a relatively new process and it has its fair share of problems. And the cause of this problem can be traced back to one unique property of metallic materials. All metallic materials are notorious for their sensitivity to external impulses like thermal cycles and stress. And in additive manufacturing, we vary parameters very widely, like we are varying 100 times the power here. And on the x-axis, we have scanning speed that is varying 10,000 times. And as a result, we get very different cooling rates, temperature gradients, and other parameters that affect the microstructure and properties and serviceability of the products. So cooling rate variations have been traced back, and this is again from one of our survey, of about 1 million times. The results are shown on the right. We can have cracking, lack of fusion of some layers, change in composition because the temperature was too high, and some elements vaporize selectively. So the chemical composition of the product was different from the chemical composition of the feedstock material that we use to make the part. Also, these surfaces are not always smooth, so we call that balling or surface roughness. And because we heat and cool these materials many times, we have residual stress and distortion, and in extreme cases, layers can be separated, like we show here a delamination in powder bed fusion for a stainless steel 316 part. So we have quality consistency issues and we need to solve them. We first go to material science and engineering. The difficulty one faces is that although we have studied for over 100 years the interrelation between process, structure, property, and performance, we still cannot relate process variables to product attributes using the theories of material science and engineering. So we need a different tool. We need mechanistic models. And in mechanistic models, we can quantitatively correlate the process variables with product attributes based on established laws of physics. And this is something that we use extensively. We have done so for many decades here. But sometimes, we don't know the mechanisms of a particular physical process. And in that case, we cannot use the laws of physics. We cannot quantify what we don't understand. So machine learning comes handy in those situations, and we can get scientific quantitative correlations based on data. And having a little bit of mechanistic understanding of a part of a problem is a plus, and I will show you why. So how do we start doing mechanistic modeling? I must start with heat transfer. And This is because heat transfer controls the microstructure and properties and serviceability of materials. And here we are solving the equations of conservation of mass, momentum, and energy in additive manufacturing. Models relate data to process and product attributes. Outputs can be used in other mechanistic models. So input is process parameters and material properties. Output would be transient temperature, velocity fields, solidification parameters, and a whole host of other things that will become clear as we move on. So what exactly are we doing? We are dividing the entire domain into lots of cells, rectangular parallelepipeds, about 250,000 of them. We are solving for 3 components of velocities, pressure, and enthalpy, 5 variables in total. So we convert the differential equations to algebraic equations, and then we do iterations. When we count how many iterations we are doing, we are actually solving about 1/8 of a billion equations per time step. For 1,000 time steps, we are doing about 125 billion total equations. Now, we don't have to reach for quantum computers. We can do splendidly with a $600 laptop. Okay, an inexpensive laptop can solve about 2 billion equations, linear equations per minute. So in an hour, we have all of the things we wanted: transient temperature, velocity field, solidification parameters, and a whole host of other things. What's the purpose? Take a simple thing like geometry. Seems very simple, right? But depending on the process variables, you can have a hemispherical pool. You can have a pool whose bottom shape is like a first bracket, or you can have one like W, depending on a parameter called Marangoni number, which tells us the intensity of surface tension driven flow, and Prandtl number, which is simply a ratio of viscous diffusion to thermal diffusion rates. And practical application of those is that, almost all metallic components have small quantities of oxygen, sulfur, selenium, tellurium, and other minor elements that love to go to the surface of any melt, and they affect the direction of surface tension driven flow. So when we consider those, having about 150 parts per million of sulfur will give us a deep and narrow pool, and having smaller amounts of sulfur will give us a wide and shallow pool. So shape and size of the pool is very important for additive manufacturing as well as for welding. So we can compute those. And here I am showing the pool geometries computed for directed energy deposition GMA that gives us a very high rate, directed energy laser that feeds metal powders coaxial with the laser beam, and thermal cycles and cooling rates are also outputs from the model. So if you compare the GMA, you will see that the pool half width is about 2.8 millimeters. Whereas if you go for powder bed fusion, the pool half width is only 1/3 of a millimeter. So it's a much smaller pool. And we are showing how a particular monitoring location undergoes change in temperature. You see, it's up and down, up and down. And if you look at the cooling rate depends on how much heat we put in per unit length. So we can compute them We can measure them experimentally. It's fair to say that models can predict these with a very good accuracy. We have done quite a bit of work on the application of mechanistic models. We provide input and we get a whole host of outputs like defect formation, residual stress and distortion, microstructural features, and also very detailed grain growth and the evolution of grain growth. So we can find and calculate many of the things that simply cannot be measured. And we need them if we need to have a pathway for rapidly solving all our problems. In summary, mechanistic models can connect process variables to product attributes via physics-based models. And example would be solution of equations of conservation of mass, momentum, and energy. So we solve Navier-Stokes equation, energy equation, and mass conservation equations. But the problem here is sometimes processes are too complex and we cannot simply quantify them on the basis of laws of physics because physics is not understood. In those cases, we use machine learning, and these are data-driven relation with or without physics. We managed to include at least some amount of physics, and I'm going to give you some examples. Another attractive feature for using machine learning codes is that we did a survey and we published it last year in Nature Reviews. We learned that there are a whole host of open source programs that anyone can download. There is no cost involved. And most important, they have all been used already in additive manufacturing. So it is there just for asking. And if you look up our review, you will find all of these examples where people have used it for solving a whole variety of problems of additive manufacturing. I want to show you two examples. Take, for example, cracking. It's a persistent problem in the metal additive manufacturing. If you look at all the raw variables, I don't want you to read all of them, but believe me, there are 12 variables, raw variables, that affect cracking. And if we wanted to investigate these experimentally by trial and error, 12 variables with two-factor design of experiments will require a minimum of 4,000 experiments, 4,100 here. And remember, these are slow processes, so it will take forever. And it's not going to be inexpensive because metal printing machines can cost upward of $1 million. So we converted them to physics-based variables, just 4 of them. Now, instead of 4,100 data points, our minimum requirements was about 16. We have well over 100 data points. We developed a cracking susceptibility index that was just published last month in Acta Materialia, and we found that solidification stress is the most important variable for controlling cracking in metallic parts in aluminum alloys. And the least important factor was the cooling rate. Engineers can use these to control cracking, but how do I know that the cracking susceptibility index that we developed based on data science actually works? So I'm showing you how we validate it. We plot cracking susceptibility index on the y-axis and number of data points, and you can see that Samples that had cracking susceptibility index greater than half showed cracks, pronounced cracks. And the samples that had much lower value, we did not see any cracks. So 4 mechanistic variables can clearly delineate cracking from samples where we did not see any cracks. So it is verifiable, it is user-friendly, and it is based on scientific principles. And we can even convert the CSI to maps like laser power, preheat temperature, scanning speed, laser power, and plot contours of the crack susceptibility index. The green areas are good. The areas down below 0.5 that has higher cracking susceptibility index ranging from 0.5 to about 1, they are red zones. They are not good. We have verified those with experimental data to show that these maps are reliable and therefore they can be used on shop floor. Another persistent problem is surface roughness. If we go very fast in additive manufacturing, sometimes the tracks break up and they form balls like I'm showing here. So again, we use similar methodology to create a balling susceptibility index, and we verified that by looking at actual data for a large number of alloys that are listed here. So there is a very clear delineation in Marangoni number which represents the strength of surface tension driven flow and solidification time. This is in seconds. So these are computed from our heat transfer and fluid flow model. So we can avoid balling using this theory. So examples of machine learning, there are many, and you will find many other examples in our Nature Reviews paper published last year. Like here, this is the result of a thermocamera experiment. This is the trace of the solidus line of this alloy. And if we plot it as a function of this angle theta, we get a feature like this. And if we separate that feature using support vector machine, we can have it classified into safe region and not so safe region. And we can take a sample to see that unsafe regions do have defects. If you look at different stages of additive manufacturing or metal printing, ranging from product design to process planning to production monitoring to control of defects, microstructure, properties, inspection, and performance, our review will give you references where all of these features have been controlled using machine learning. So I want to summarize and also talk a little bit about the outlook. The application of machine learning provides quality improvement without trial and error. And this is very important because trial and error has worked for welding and for casting, but it will not work for metal printing because metal printing machines are so expensive and so slow. So it's going to be time consuming and expensive. Also, it can give us material selection based on scientific principles, so we can avoid defects. And this is based on proven results, so it will give us better product performance and easier product qualification. Future technologies like additive manufacturing will mature with less empirical testing, and it will mature much faster than welding and casting did because there was no digital tools 100 years ago. Now there is, so we must take advantage of those digital tools. And my final comment is that all researchers with a $600 laptop can contribute. Those who have got good ideas can test their ideas. So we can benefit from the ideas and works of more people. So it will make the world a more inclusive place and a better place for all.